Welcome everybody to this evening colloquium. On behalf of the Institute Colloquium Committee, we are presenting this talk today by Professor Sriram Ramaswamy, and very, very happy to have him here. He's actually visiting us for 1 week as a distinguished visiting professor. Very, very brief introduction. Presently, Sriram is an honorary professor and J.C. Bose Fellow at IISc Bangalore. And in between, he had been the second director of TIFR Hyderabad on interdisciplinary sciences. And then he came back to IISc again. So Sriram is famous for non-equilibrium physics and active matter physics. He is basically the pioneer of this, one of the pioneers of this field, which talks about motility of many self-propelling systems, both living and non-living. Self-propelling meaning they consume energy from the environment and produce their motion. And in particular, he is famous for formulating the hydrodynamic equations, which describe these systems as a continuum systems. And these equations address alignment, flow, mechanics of these complicated systems. And okay, and rest you will hear from him. So Sriram started his journey at University of Chicago. He got his PhD in 1983 in theoretical physics. And then he did his postdoc at UPenn with Professor Tom Lubensky. He was there for 3 years. And 1986, he joined IISc, and he had been there ever since then. Sriram got many, many awards. He got Shanti Bhatnagar Award in 2000, Infosys Prize in Physical Sciences in 2011, and then he was the elected Fellow of Royal Society in 2016, and in 2016 itself he got H.K. Firodia Award. So welcome, Sriram, please.
First of all, thank you very much for the invitation to give this Institute Colloquium, and thank you very much to the Physics Department and IIT Bombay for inviting me to be a distinguished visiting professor. I think this is the first time I've been a distinguished anything, I'm not sure. So I'm really honored, I'm really delighted, and when Anirban and friends said that they'd like to invite me here, I said yes immediately, because it's a place where I have a lot of friends, both scientifically and otherwise. And I'm having a ball here. I've been here for now my third day, and I've been having a fantastic time scientifically talking to people. Today I'll try to tell you a little bit about what I work on and why I think it's fun. So let me try to do this in a rational way. Okay, so when you give lots of talks on a subject, you recycle some of the material and try to give people the impression it's a different talk by changing the title. So I've duly done that. So I'll spend the first, not 1/3, first about 10 minutes or so, I'll tell you what the field is about, I'll give you some background, and I'll very quickly tell you sort of old results, because I started working on this stuff really a long time ago, more than 20 years ago, and I've not been able to find my way out of it. And I hope I can convince you that it's still worth working on this stuff. And after that, the core of the talk will actually be very new work. 2 of them are preprints, and a third is not even a preprint. It's a sort of fond gleam in a parent's eye, and then I'll summarize. So the core is a little technical, but we are the Indian Institute of Technology, so I am assuming you guys can handle it. Okay. So what am I talking about? What is this active matter? See, basically, if you have, take this object and take this arm, what's the difference? They're both made of particulate components. In this case, you will naturally say the components are molecules or something packed into a crystalline lattice or something amorphous, as the case may be. And here, it's natural to think of this stuff, the quote-unquote atoms of a chunk of living tissue, as being cells. And what's the difference between a collection of cells put together and a collection of dead particles put together? It's the cells are, in a certain sense, alive. They're alive. And what that means is that they are powered in some way. Each of them receives a sustained supply of chemical energy, of free energy, which it turns into work in some way. It does many things, and I'll only talk about some of the things. But basically, the difference between a chunk of living matter and a chunk of dead matter is the living matter, first of all, is kept alive only by a sustained input of nutrient. And that means that you can think of it as made of components, each of which carries a dissipative arrow of time. It's constantly taking up low entropy stuff, doing something, spitting out high entropy stuff. And it stays that way only as long as you keep that sustained supply on. Okay? So, and collections of particles of that sort are what we call active matter. And my talk really isn't going to be about the biology of these systems. It's just that, look, I am a condensed matter and statistical physicist. And my question is just, how is a chunk of active stuff different from a chunk of dead stuff as a piece of condensed matter? And that's really what I'll talk about. And with some luck, that essential difference is what drives the function of living matter as well. Okay? This is by no means a new viewpoint. Lots of physicists jump into this field because living matter and its imitations are the most profoundly non-equilibrium kind of matter. Some of them go very far in the direction of biology and really do things directly of relevance to biology. There's an eminent former condensed matter physicist in this room sitting there who moved from superconductors to molecular motors and has done a fantastic series of works on the subject. So now, again, I'm talking mostly to the students in this room. So you guys all learn statistical mechanics. And you learn, the simplest thing you learn about is you have an isolated system. And the next simplest thing you learn about is a system which is a piece of an isolated system. So here you look at the whole system, it's isolated, and you can do StatMech on it, which if you're lucky enough, it's somehow distributed uniformly over all microstates consistent only with a constant energy. You can do this kind of statistical mechanics if you look at a piece of that system. This piece and the rest of it can exchange energy, exchange particles, exchange volume, if you like. And the sum of those two is constant. And so this system, this subsystem, is characterized not by a constant energy, but a nearly constant energy. It fluctuates and it has a temperature. This system and this system both have a temperature, but this guy is characterized by a temperature, its energy changes. This guy is characterized by an energy and its temperature in principle fluctuates, but around a mean. And for very, very large systems, it makes no difference whether you look at this or this. All you guys who've taken any kind of elementary StatMech or thermodynamics course know about this, okay? And you know the rules of the game. Basically, if you want to figure out what kind of state of organization do these kinds of systems settle down into, they settle down into a state characterized by maximizing their entropy subject to various constraints. It could be constant energy, number, whatever it is. And that leads to this familiar law for the subsystem, which is e to the minus energy over kT for configurations. And the only technical difficulty is sometimes how to solve, calculate partition function, calculate order parameter, those kinds of things. The principles are known. These systems have a statistical steady state with a very important property. Namely, it's invariant under time reversal. What it means is that if you took, you can start out one of these systems in some weird initial state and it will move around, but eventually it will settle down into a state where basically there's no narrative. That is, if you play a movie of that system and you play the time reverse of the movie of that system, you will not be able to tell which it is. So which means you can't sell it as a movie to anyone because you don't know which side to put the end in. Okay? What we are interested in is these kinds of systems, driven, active, living systems. So you have a sustained input of energy, the system does something with the energy, spits the energy out, and you maintain it in that kind of state, okay? And so these systems can also settle down, reach a state which you might be tempted to call equilibrium. Physicists don't call it equilibrium, they call it non-equilibrium but stationary states. And the point about these states is they are time translation invariant but not time reversal invariant, okay? And all the fun happens because of that. And the trouble is that for systems of this sort, we don't have a magic formula, a general rule. That's what makes them interesting, that's what makes them difficult, and that's what gives them a huge amount of potential to do things that you wouldn't otherwise have guessed at. Okay, that's a very long introduction. And the kind of questions we'll ask is this, imagine a collection of hard spheres packed in a box, and imagine instead a collection of ladybugs packed in a box. Imagine a polymer melt, and imagine instead a snake pit. So the kind of question that I, as a condensed matter physicist, I'm interested in is how are these guys different from these guys? Okay, what are the general laws governing these, and in what ways are they different? What kinds of weird things can happen here that can't happen there? And finally, of course, how does that connect to life? Now, in addition to real living systems, you can make artificial active systems in many different ways. Okay, the basic idea is, let me give you a specific example. Supposing you have a bottle full of a compound which is in a state from which it actually wants to decay, but it's stable enough that if you don't do anything very drastic to it, it'll sit around that way. So for example, a bottle of hydrogen peroxide. Supposing you put into that bottle of hydrogen peroxide a little particle which has a catalyst. And in fact, let's take this specific case from Ayushmann Sen's work of a catalyst, a particle half coated with a catalyst. So what will happen then is that this guy, when it makes contact with the catalyst, with great certainty, it will decompose. Okay? So that means as long as you maintain a background concentration of the metastable compound, this particle will have a very funny property. Along its surface, there'll be a compositional gradient. And as long as you maintain this supply, that particle will permanently have a composition gradient. And therefore, what happens if you've got, think of a composition gradient as just, imagine that this particle has a different size from this. Imagine these are big hard spheres, and each one becomes two little hard spheres. So what you have is more big hard spheres here, and fewer little hard spheres, more little hard spheres here, and fewer big hard spheres. The result will be osmotic flow along the surface of the particle. That means the surface of the particle will act as though somebody is sweeping fluid past it in a little layer just as thick as the particles. So it will act as though it has cilia. So it will act like a swimming organism. And so these guys swim. I don't have a movie of that. And these Ayushmann Sen and others have done fantastic work on these kinds of systems. In a sense, this embodies in a very, very rudimentary way the essential physics of any chemical engine, right? It's a system which has a catalytic process, and that catalytic process is coupled in some way to movement, and that movement, if it's on a track or something, leads to the thing walking, running. So Roop Malik's molecular motors are doing something like this, except not in a fluid. But you can imitate active motion in many different ways, and these are all serious, faithful imitations. For example, what you have here is something from the PhD work of someone else who's in the room, namely Nitin Kumar. So you've got a little particle. You are looking at it from the top. So on this surface, I place an object like this, whose front end and back end are different. I place it on here. I shake that table up and down. Imagine just tossing that table up and down. This particle has different mechanical properties at the two ends, and the result of your shaking it up and down, you don't pick any direction in the plane, you don't push the particle, is that this particle walks. And I claim this is actually a valid kind of active matter system because the global vibration of the table is some kind of nutrient bath, and the particle's shape and its coupling to the base enable it to act like a ridiculous little motor. Okay, and you can do a lot of fun things with this. Okay, collections of active particles can do all kinds of things. Those funny colloids I talk about can form organized structures, can form layers, stripes, patterns, can condense in various ways, can undergo analogs of gravitational collapse, can display analogs of plasma oscillations, can display sustained oscillations, and so forth. So all kinds of spatial organization can happen. If the particles, in addition to having self-propulsion, have some non-trivial shape, like they're elongated, they can form weird liquid crystalline phases, which in turn whose self-generated flows can create weird kinds of turbulence-like phenomena, not governed by what governs usual hydrodynamic turbulence, but governed by their self-propelling activity. So just as a playground for studying spatial organization in systems out of equilibrium, active matter is a great system. while studying these systems, one important thing to keep in mind is you have broadly two different domains in which you can look at active matter. One is, if you've got a herd of cattle in a field or something, it's true that each cow, when it walks, pushes the earth backwards, and that is affecting other cows, but it's doing so in a very trivial, global, rigid way. So the fact that the momentum of the cow plus the ground is conserved doesn't really lead to dramatic interactions amongst different cows, because the medium they're walking through is not highly deformable. It's the earth. If you're walking in a much softer medium, to take the extreme case, if you're moving through a fluid medium, then if you swim, you push the fluid and that fluid pushes other things. The slower you swim, the longer ranged and more nearly isotropic this interaction is. You know that small microbial swimmers have a flow field which decays very slowly with distance and which talks pretty much in all directions to other neighbors. The faster you swim, the more this hydrodynamic effect is swept into a narrow wake behind you, and the less important that interaction is for many purposes. But broadly, we therefore distinguish dry and wet active matter according to whether your dynamics is taking place on a kind of inert substrate or a fluid medium or something more complicated. This subject could actually have been old hat by now, because people in the late 1960s wrote a beautiful paper which to this day is almost completely ignored by most people in the field. They thought about all these questions and it sank without a trace. I think it's cited about 30 times or something in the literature. And these guys even used a term that we thought we invented. Okay, so they stole it from us backward in time. And so I think it's a nice example of the history of science. The ground wasn't ready because the formalism that we use, namely using hydrodynamic theories to describe things more complicated than a simple fluid, those things hadn't been formulated. People hadn't invented the hydrodynamics of liquid crystals. People hadn't said, look, we can take complex systems, magnets, all kinds of things near their critical points and write down continuum theories. We can do the statistical mechanics. We can do the time-dependent stat mechanics. That whole literature didn't exist yet. It came along just a few years later, and nobody paid these guys any mind. In any case, in general, however, in a different domain, in sort of fluid dynamics, the hydrodynamics of suspensions of swimming organisms is a subject which is pretty well developed, but in a slightly different language. They came close to talking about the kinds of things we talk about. Again, I mean, there's a nice point to keep in mind. The place where a lot of this stuff, this kind of microbial hydrodynamics is pursued, is a place called the Department of Applied Maths and Theoretical Physics. So that's a building called Applied Maths and Theoretical Physics. What they have in there is experimental fluid dynamics, among other things. They also have, people who do string theory and all those things. But the really cool stuff is this. Again, to the students. So, okay, so let's now ask ourselves, supposing somebody gave you one of these systems, what would the equations of motion, of a collection of moving self-propelled things look like, and how would it look different from dead stuff? How do you build equations of motion for these systems? The way you do it really is the following. The general formalism. I'm going to use up all my time on general formalism. Dead. Any sort of chemical machine can be thought of in this way. That you have a chemical process which you drive in some direction. What is this X? X could be how many fuel molecules you have converted from fuel to waste. Okay? So that's how ungreen you have been. This is an abstract image to tell you that motion in this direction is coupled to motion in this direction. I apologize to friends of mine who have been to many of my talks and have seen this slide before, but hopefully there's some in the audience who haven't. So you push the system in the chemical direction. What does it mean? You go, as the system consumes fuel, you keep topping up the fuel tanks. You maintain the system in a driven state. And something about the internal works of the system, the real, the business of the system, couples that to spatial motion, okay? So this is the picture. So what that means is I should be able to build equations of motion for systems of this sort by saying I have a system with some degrees of freedom which I keep track of, physical degrees of freedom, and I have a chemical degree of freedom. The reference system, let's say, is one where I don't force the system in this direction. I just keep everything at thermal equilibrium. So if you think of chemical fuel, imagine that the conversion of ATP to ADP and inorganic phosphate and energy, you study it on such long time scales that keep it at chemical equilibrium. It's infeasible in the case of that particular system, but you can imagine some reaction studying in both directions. So then what you'll have is, you'll just have the equilibrium dynamics of the physical and the chemical variable at some temperature. For those of you who like equations, you can write Langevin equations for that dynamics. And the chemomechanical coupling is that the chemical force, the derivative of the energy with respect to the chemical coordinate, can be coupled to the physical motion. This is just a re-description of what the physical system does. You shouldn't think of it as a theory. It's more like a recasting. So you have chemical force drives physical coordinate, physical force drives chemical coordinate, and you have a certain coupling here. If that coupling depends on the physical coordinates, then holding the chemical force constant will mean that there'll be terms in the equation of motion for the momentum of your physical variable, which are of a sort that you would not have had if you weren't driving it. And they are constrained only by the spatial symmetries of the problem. So this delta mu, the chemical force, you can think of it in the specific context of ATP, the chemical fuel of the cell, as the chemical potential difference between ATP and its hydrolysis products, for those of you who know that kind of language. And you can build equations of motion from this general principle, and what that amounts to saying is, you can take the original equations of motion you had and augment them with pretty much anything you like that is consistent with the spatial symmetries, let us say isotropy, parity, whatever it is, those kinds of things. You can generate quote-unquote new terms in the equations of motion. So this sort of, this gives you a sort of lawless terrain where you can do practically anything you like, as long as you know what you're doing. Okay? And so we started doing, this way of describing it was first put down in a nice way by Curie-Dresden group in the context of describing molecular motors. But you can use the same principle to write down equations of motion for very general systems. Sorry, neck is hurting. So now a quick recap of stuff we did like 20 years ago. We showed that if you write down the equations of hydrodynamics of a collection of organisms which have built-in stresses and an orientation, so a living liquid crystal, what we showed was systems of that sort simply can't stay aligned. If you align them, if packing makes them aligned and you let them start swimming, small perturbations about the swimming state give rise to secondary flows because of the stresses they carry, which invariably destabilize them. Depending on the type of swimmer, if there's a swimmer that does a kind of breaststroke versus a swimmer like a bacterium which pushes fluid and moves forward, they go unstable in this failure mode or in this failure mode, splay or bend. We also showed that the mere presence of swimming activity in a fluid changes the effective viscosity of the fluid. This is all back in the day, we also showed how to make artificial active matter systems that do things like this. I'll show you a slightly weirder example than average. This was Vijay Narayan's work from 15 years ago, where he showed that you can make particles that have more kinetic energy for their motion along the length than transverse to the length. It's as though these particles carry two temperatures, one longitudinal and one transverse, which of course is not equilibrium. Each of them doesn't on average travel anywhere, not like it's walking, but these are non-equilibrium in a funny kind of way. Nitin looked at particles that walk in that direction, and when he put collections of them together in a medium, he showed that they can talk to each other through the ambient medium and self-organize into flocks. There. We showed that structural defects in aligned states of these systems, if they have a certain asymmetry, if one end is different from another, like this type of defect, actually self-propel. So structural defects become self-propelling particles. So if you focus on this bit here, you'll see there's a defect here which is walking this way, this way, this way, this way. And the other kind of defect, which is threefold symmetric, just sits there. So this is just to give you a quick recap of the kind of fun we had. And we use this to make a defect unbinding theory of the transition from the liquid crystal ordered state to a disordered state in these active systems. And this, so I'm mentioning these because these few, yes? Was there a question? It's just an echo. I'm mentioning these because these little themes from our fairly early work have turned out to, in many ways, guide even the sort of research that people are doing in these problems today. Not to boast, but just to give you an idea of the long reach of good bits of science. Okay, so that's the introduction and background and earlier work. So I guess in the next 25 minutes, I'll tell you about what we've been doing more recently. I told you that aligned states of swimmers tend to go unstable. So what we started looking at recently is the recently meaning this paper I think was posted a few weeks ago or something, with Purnima, who's a student at TIFR Hyderabad, Prasad, who's on the faculty there, and Navdeep, who was a student and now is a postdoc in Göttingen. We started looking at collections of swimming things with an orientation and a concentration and a flow field. So there's a fair amount of maths. The idea basically is you start with the physics of flocking, where you have a rule-based interaction. This is each of these guys looks at its neighbors and tries to align with them. At high enough concentration and low enough error rate, these objects form a flock. If you add in fluid flow, as I just showed you, that cartoon I showed you a few slides ago, that aligned state goes unstable. What we showed is that that picture is modified if you take into account the inertia of the system, because the flow fields take time to kick in, and if the swimmers are fast enough, the instability starts to grow and starts to spread, but swimmers, if they swim fast enough, can outswim their own instability. And the combination basically is the speed of the swimmer, V0, divided by a speed scale you can make from the stress these swimmers create and the mass density of the fluid. So what you have is that madly unstable region is down here, and if you are swimming fast enough, you can escape your instability. So this is an example of a hydrodynamic instability in which you're, for those of you who are into hydrodynamics, you're unstable at low speeds and you're stable at high speeds. Inertia stabilizes instabilities that kick in the Stokes limit. Okay, all of this story, this came out a couple of years ago, was without worrying about the concentration of the particles, where the particles are or aren't. So let me skip. Well, you can write down the equations of motion for the concentration. If you only have the concentration and a vector field that tells you which way they point, you have some kind of dynamics for that vector field, which consists of two parts: a tendency to align and a tendency to carry itself, because that which way they point is also which way they move, and a tendency to carry the particles. This dynamics gives you waves because concentration fluctuations reorient the orientation transports the concentration. This interplay gives you waves in the aligned state. If you include the fluid, then the orientation can be carried not only by itself but also by fluid flow, and the stresses drive fluid flow. So this coupled dynamics turns out to give you a new kind of instability whose pictorial description is a little difficult, but what I can say, I hope I have, yeah. So now what happens is, supposing you've got a state where, I don't have a blackboard, no, I guess I do. Supposing you have a state where these guys locally are all lined up pointing in some direction, and supposing I now perturb it slightly like this. Then two things will happen. One is that these guys will try to reorient because of their interaction. The other is this deformed state will generate fluid flow. And that fluid flow, with an inertial lag, will also try to reorient these guys. So you have this wave-like dynamics that I described here, competing with the reorienting dynamics of the fluid flow. The two timescales aren't the same, so you perturb, They're coming back, and the flow then comes along and can destabilize it. So now you have a new kind of instability in which you'll get waves, and those waves will get stirred around by the fluid flow. And I can't describe it better than that. I don't. Yeah, but you can instead watch the movies. What you find is a steady state in which you've got an aligned state, which without your putting in any disturbance other than an initial deformation, without your putting in any noise, spontaneously goes into a state where the splay and concentration keep on beating against each other, and you get this sustained waves. If you go a little further, those waves, those disturbances start to get more and more disorderly. And if you go a little further, you get a weird kind of turbulent state in which concentration waves go around all over the place and completely disorder the system. So this is sort of our latest instability of active liquid crystals. We don't know yet of a good experimental system in which to look for this, but we're hoping someone else will solve that problem for us. There's all kinds of interesting turbulence-like features as a function of length scale, which I will not get into. Okay, so that's one story. So after my introduction, I've told you about a new kind. I also tried to give you a kind of idea of how we describe these systems. We don't go in and describe where every particle is. We write a continuum theory, which look, there's an orientation field, there's a concentration field. The orientation field, the concentration field, you describe its dynamics by saying the number of particles is conserved. So the transport of particles has some current. Then you describe how the orientation affects flow by saying, look, I just need to write down what the stresses are. Those stresses drive flow. I patch these together, and without fine, detailed knowledge of my system, I can actually make predictions about their dynamics. So that's story one. Let's switch to a very different setting. Still motile particles in a fluid. There's a thing called caustics. What's a caustic? A caustic, you see it in optics when you look at light rays reflected or refracted from curved surfaces. The general way in which light rays focus is not to a point, but to curves or surfaces. And those are called caustics. I don't have a picture. Shocking. I'm sorry, I missed it. Okay. In optics, the envelope of reflected or refracted rays, the word caustic comes from the fact that focused light burns. Okay, which I hope all of you have tried to experiment with when you were young and unsupervised. And at a caustic, the intensity diverges. You can get caustics in particle motion. Let's take a very, very, very simple-minded picture of phase space. Phase space meaning position x and momentum t. And imagine at some early time, you've got particles distributed in phase space like this. What does that mean? That as a phase space is xp space. So that means you've got particles over here with a larger speed than particles over here. These guys will then overtake and eventually enter a state that looks like this. In a state that looks like this, the real space density, which you get by integrating over the momentum, will then, if you have a structure like this, acquire a singularity. You will get a density concentration at these points. So this just tells you, this is like in traffic or something, if you've got stuff behind that's moving faster than the stuff in front, you will get a pileup. Okay? This is just the physics of that pileup. If fast movers initially behind can catch up. Why am I telling you about this? Actually, because particles in fluid flow can in general get swept up by the flow and create caustics. Those caustics matter because it means you're enhancing the probability of encounters between particles. So that can matter for things like rain, as someone in the room knows very well. But it can also matter if the particles are actually alive, because then they can meet up with each other, they can communicate, they can reproduce, all kinds of things can happen. So recently with Rahul Chhajwa, Rajarshi and Rama, we started worrying about this class of problems. And so what we did was to write down the equations of motion for a particle with position x. Imagine a bunch of independent particles with position x may be pushed by some external force field. Let's say I forget about the inertia of the particle. I say it has a velocity which is some inverse of friction times a force. It's moving, it's carried by an ambient flow, and it propels itself through the fluid because each particle, let us say, carries a little vector, W, which tells you which way it's trying to move. So W is which way it's trying to move. This vector, in turn, is affected by the ambient flow. Let us say this vector is trying, maybe is proportional to the extension of the particle. It's trying to relax off to 0, let's say. It's rotated by vorticity. It is stretched by the extensional part of the flow. It responds to local curvatures in the flow, and it's kicked by noise. You can patch this all together. It turns out that the equations for particles of this sort, when you completely neglect the inertia, the mass of the particle, can be turned into a form which looks very much like the equations for dead particles with inertia. Okay, I won't trouble you with the dynamics, just tell you, with the details, just tell you can do it. You can solve for the dynamics of particles of this sort in a specific flow field. Let's say you take a flow field which is just a point vortex. Where is my equation with the point vortex? It's not here. So imagine you've got this particle in a flow field of a point vortex. Okay? So swimming particle, what's it do? It's trying to follow its nose and swim. Depending on the details of how its extension relaxes, it can either relax to 0 or it can have a preferred length and tumble and roll around. Flow reorients it, and the particle goes where it's pointing, but also is carried by the flow. This coupled dynamics, it turns out, gives you behavior. So this is in the presence of that vortical flow field. You find something quite analogous to centrifugal pushing out of particles. You actually get a piling up of particles, and it looks surprisingly similar to the dynamics of dead particles, but with actual mechanical inertia. Okay? And you can work out what the number density of particles will do. You can work out conditions under which caustics will and won't form. You can plot position against time of these particles, and what you can see is these whirl lines accumulate over here with a structure very similar to optical caustics. The maths of it is interesting, but I worry that I will have no time to talk about the other topics. So I'll just tell you there's nice maths having to do with singular perturbations. Basically, in this same flow field, if you start beyond a critical radius, you don't get caustics. If you start close enough, you get caustics. And the underlying physics is indeed that stuff inside is moving faster than stuff outside and can catch up and cause a pileup. Okay. You can do this for different kinds of particles. And now what you can do is, rather than one vortex, you can take a collection of such particles and put it in a turbulent flow. So you create a turbulent flow by solving the Navier-Stokes equation with some forcing. And in that turbulent flow field, you chuck in a bunch of particles and ask where they go. And what you find is, again, two things matter. One is self-propulsion relative to the ambient flow, and one is the degree to which the particles respond to curvatures in the flow. And what you find is there's an optimal value of this tendency, which is, I'm sorry, I have to go back to the equations, the degree to which the orientation responds to second derivatives of the flow, that is curvatures. If you have, again, try to draw this here. If you've got a particle with some shape like that, and you create a local flow field whose value is varying like that, that flow field will orient this particle's orientation vector. And that, apologize for being technical, is this coupling. These are the two key ingredients that matter. So how fast the particle is moving relative to the ambient flow, and the coupling of flow to orientation in this sense. And what you find is that the particles accumulate in regions, their particles are centrifuged out of vortical regions and accumulate in regions where the flow is extensional. Okay? And the degree to which that happens has an optimum as a function of this funny coupling. Okay? And you can analyze it statistically in various ways. which maybe I'll not spend that much longer on. In particular, what you can show is that the tendency to accumulate in regions of strain sort of is largest at an intermediate value of self-propulsion. Okay, all right. So that's end of story 2, and I have left myself some 15 minutes for story 3. So let me see how well I do. So story 3, the first 2 at least exist as more than a fond gleam in a parent's eye. There are preprints that you guys can read. This one will be posted reasonably soon, but isn't ready yet. Okay, this is Roshan's PhD work. It began with Rahul Gupta and Harsh. Roshan is a student jointly with Ajay Sood. And you can imagine what I am having to deal with looking after an experimental student, given Ajay's responsibilities. So I already told you about this model system. This is a vibrated surface on which I put particles, and the particles walk. And we've done a bunch of things on this problem over the years. The experimental setup looks like this. It's an industrial shaker. The dimensions are all very macroscopic. The particles are half a centimeter long. The container is about 10 centimeters. The sample cell is about 10 centimeters. And these guys, when you shake up and down, these guys walk, like I told you. And you take pictures from the top. I thought I had, well, it doesn't matter, okay. Oh yeah, I did show you already. So in this system, we study this system in the following limit. A very small number of these elongated particles that walk, and quite a large number of these round particles that just sort of jiggle around and don't do much. As a function of, so keeping the concentration of the motile, the self-propelled particles, constant and really small. That's an area packing fraction of 6%. We increase the concentration of these beads from about 0.5, 0.7, 0.75, 0.77. And what you find is that these guys, here it's sort of a reasonably fluid system. Here these guys undergo flocking, which I'll just show you. Then these guys start to cluster. Eventually they self-organize into a little interface. And what happens here is these pointy particles are all pointing this way. Their tails, their fat ends are here and their skinny ends are here. And they push the beads into a corner. So what that means is that they create a segregation between bead dense and sort of bead rich and bead poor. They make these round particles whose only interaction with each other is that they can't go through each other. They create a condensation, low density, high density. This is, of course, a fairly undramatic image of the concentration, except for the tricky little interface. But so just to show you, isotropic, ordered, clustered, and these guys have actually pushed these guys into a corner. Okay. So you can do this in slightly different geometries if you like. And it's slightly more dramatic here because what happens is isotropic, again, ordered, and now look at what's happened. These guys have come in from two sides and they've captured this batch of beads. So they've not only made it condense, they've actually immobilized it. So, and that's a snapshot, maybe a little bit of time averaging, but here is what it does. Let me play it again. So yeah, the dynamics is too quick. I think in this particular one, yeah. So, but I mean, what I want you to focus on really is this sequence: isotropic, flocking, and captured. Yes? Yeah, I'll try to show you. I think I have a better movie where you can see it. There is a kinetics, and the question of what that kinetics really is not. So I'll come to that in just a minute. You can build a theory in the following sense. You can say, look, I mean, I don't want to do details. There is a density field of beads. There's a density field of rods. The rods have a speed V0. the beads have some velocity field v. So you treat the beads as a kind of fluid. Okay. The rods have an average, a vector field p, which describes locally how the rods are oriented. And the idea is the following, that if you've got a region where the rods are pointing in some direction, they're moving and they're pushing the beads. And how well they couple to the beads depends on how dense the beads are. Okay, so you can see that in these, you can see that to some degree. Yeah, so you can see that as the rods move, they really are pushing the beads. Okay, and the higher the packing of the beads, the more effectively they're able to drag the beads. So that is this bit, that is, the beads diffuse left to themselves, but are also pushed by the rods. Okay, and this coefficient is positive, meaning that if the rods are pointing that way, the bead current is that way. And what this means is that supposing I have a uniform region of beads and I have a bunch of rods pointing that way. If the rods are pointing that way, they'll move beads from here to there. That means the rods will create in their vicinity a bead density gradient. There'll be higher density in front of them than behind them. Okay, so that's part one of the story. Part two of the story is, given a density and homogeneity of the beads, what do the rods like to do? Supposing they weren't moving, supposing you just created some inhomogeneous, more beads there, fewer beads here. Well, the rods are tapered. There's a skinny end and a fat end. So they will like to sit with their nose. It's easier for them to sit with the fat tail in the region where there's fewer beads. So on the one hand, the rods create a density gradient. They bulldoze the beads in front of them. On the other hand, that's how they're happiest. So this positive feedback means that the system should spontaneously go into, if this effect is strong enough, it should win over the tendency of the beads to diffuse and create an instability. So if you do the math, as they say, you can do the math. It's very easy. I've pared it down to its essentials. This part is rods push beads. This part is beads. Rods. This part is rods like to align with their nose pointing towards where there are more beads. There's actually a third part, which is that which way the rods point is also which way they're moving. So confronted with a bead density gradient, the rods will tend to move towards where there are more beads, but they're going to start slowing down because this parameter, this self-propelling speed of a collection of rods, is going to start getting sluggish once there's a lot of beads. So you're going to find that they actually pile up against where there are beads. So, the self-propelling velocity goes down with bead density. So if you do this, you get a diffusive instability, that is with growth rate proportional to wave number squared, with a coefficient that depends on the product of these two tendencies, rods pointing to beads and rods pushing beads. And you get a pileup of rods at the edge. Now the question is, how far can this go? Well, it turns out this is actually pretty wild. What happens, this again is experiments, even when you dial down the concentration of rods to this low, you can create a condensed state. Okay? So these guys, it should really worry you, because what I'm saying is that, normally if you have a thermodynamic system, you need something extensive to have an extensive effect. It looks an awful lot here as though a sub-extensive number of these active guys, a finite number, is enough to influence all those guys. It's not at all obvious what will spoil this. We haven't yet figured out what will. Okay? But it's fun to watch the process anyway. So watch it. So this tiny population of motile objects is able to herd and mobilize this entire collection. So, my little argument of a kind of diffusive instability, spinodal decomposition, something like that, isn't the full story. First of all, it's not as though there's enough rods to. First of all, you don't see the beads accumulating into some kind of modulated structure like you would in unstable growth, phase separation, spinodal decomposition. You don't see any of that. What you see is the rods self-assembling. So all of this is the rods are self-assembling into a kind of little 1D membrane or piston or something, polarized and moving, and it can mobilize a huge population of beads. So you can ask, can we understand this a little bit better? So you can actually do, again, elementary theory. You can say, look, okay, let's do a 1D theory. So let's say you just write down a theory which says that there's a continuity of beads with a velocity field v. Skip that line. You've got drag on the beads is balanced by the force with which the rods are pushing the beads, which is a concentrated force density right here, and some kind of equation of state. You got some pressure density relation between the beads, that if you push here, how much give will you get, right? So you just write that down, and you can take this and you can solve for the steady state. So this is sort of bead pressure, drag, and forcing by rods, with some boundary condition that far away at the back. Think of a 1D geometry, not this circular one right now. Something related was done by Madan Rao and company on motile particles plowing through a bead medium. You can solve for the decay of the bead density, and you find it decays exponentially with a decay length that is set by how stiff the bead pack is. So this is, if pi is the pressure, del pi by del rho. So essentially, within a linearized approximation, it's set by how hard it is to compress these guys. So the harder it is to compress this guy, the farther out the bead density will decay. So in the limit where it's sort of maximally packed, there's kind of, the sky's the limit. A small population of motile rods can push what seems like an unbounded number of beads. So something like this is, I think, at the back of these phenomena. So, and how much this density is at this front is just set by how hard you're pushing. So you can actually solve, you can match and do stuff that's not very different from Schrodinger equation with a delta function and integrate across it. Yeah. Yeah, you get it in that also. Yeah. So, yes. I mean, I showed you, you get two things, but you can get this also. And I mean, essentially, if you like, this is the essential phenomenon. There's another question you can ask. Okay, I didn't put that in the talk. You can ask, how come you get this balance thing pushing from both sides? There, I think what's happening is the following. Supposing you have a pack nearly balanced. Supposing there's slightly more on one side than on the other. Then this thing will start to move. If it moves, it's going to liberate some of these guys. And there's a chance that they will turn around and come around to the other side. So at least around the balanced state, you can think of some kind of self-adjusting, stabilizing phenomenon which favors actually something catching it from both sides. It's a separate question then why it doesn't always happen, and I don't know. If you double the numbers here, it may be a question of there being more than one possible stationary state. I don't know. Okay. Anyway, so to summarize, I gave you a kind of background on active matter in general, and then I gave you three very specific and I think from one to the other rather different examples of the potentialities of active matter. Just now I told you about how it looks like a sub-extensive number of particles can condense an extensive number. I don't know how far you can push that. I told you how you can get caustics in self-propelled particles in flow. Even you can get centrifuging and effects of that sort, which normally you associate with particle inertia, instead thanks to self-propulsion. And then early in the talk, I told you about how you get a weird new kind of concentration wave turbulence without the active stresses that were at the back of that initial instability I showed you. And I also titled the talk, so I saved a couple of minutes for this. I gave you a title that said today and tomorrow. I mostly told you about today. I told you very little about yesterday. And for tomorrow, there's lots and lots of directions. First of all, this field has become very crowded, which for me isn't actually fun. Much of my career I spent working on stuff that other people thought was nice, but weren't eager to themselves jump on and start working on. So this gave me a very comfortable academic life. You guys have a very different life where you have to compete. For years, I didn't have to. This field has become seriously crowded, fashionable, and has many of the less desirable features of most human endeavors now. Anyway, nonetheless, there's lots of interesting directions to look at. One is just, the instabilities and dynamics of active matter. Most of the work that has been done has been on the hydrodynamics of small-scale, slow systems, okay? Microbial swimming, where inertia matters not at all and viscosity is everything, okay? We have started to show that there's really interesting stuff that happens when you, on scales where inertia matters. We don't have anything like the right kind of controlled experimental system, because what you really need, you saw that, I showed you how if you swim fast enough, you can stabilize flocks. So then you need you need either a knob or you need a set of otherwise identical systems in which the velocity is, self-propelling speed is different. Nobody has really bothered making them. There are some efforts in that direction starting. As also recently, I was at a workshop at the Newton Institute where they had assembled a very disparate collection of people with my kind of specialization, people who work on really classic turbulence problems, people who look at underwater staircases in the ocean, people who look at the red spot of Jupiter. They had put all these people together in the fond hope that something new would come out. I don't know if it would, but the result of that program, which you should take a look at, and it's still going on, is that there are interesting connections between the kinds of turbulence and kinds of patterns that we talk about in active systems and what you see in more conventional driven hydrodynamic systems, where the driving is externally imposed by temperature gradients or imposed flows and so forth. Secondly, one of the things you would like to do in active matter to make an impact on living system physics is to be able to control these active agents and take into account the fact that living self-propelled particles are not only motile but respond to signals and send out signals and process information and so forth. There's of course again starting to be a lot of work on this. This is something that Kabir Hussain, Madan Rao, and to some extent I did, but there's this field again has got crowded, but there's, I think, many opportunities to look at active systems with information processing. There's sort of Bangalore science, I forget what the expansion, BEST cluster, Bangalore something science and technology cluster. Anyway, there's an initiative funded, I guess, by SERB or by the PSA's office. I'm not sure where the funds come from, but there's an initiative to harness some of these ideas to do something with them. You should take a look at that and integrate ideas of whether the kinds of approaches we take to active matter can be useful in understanding collections of motile things that signal to each other, assemble things, carry out tasks, and so forth. Also, living matter doesn't just move and doesn't just process information on an instantaneous time scale. It does it on an intergenerational and epochal kind of time scale. So studying evolving or evolvable active matter, again, to some extent, Shashi Thuttupalli has done some things like this. That's another very big open direction. Also, when we wrote down the equations for active systems, we just said, look, the rules for choosing the variables are the same as the rules we already know and love from looking at equilibrium ordered systems. You look at conservation laws, you look at broken symmetries, you look at what variable is going critical or something at a phase transition, and so you use those variables the same way. But in living systems, maybe because of evolution, some living systems have evolved to where their natural set point is such that some variable is near the threshold of an instability all by itself. There's large amounts of anecdotal evidence that many living systems seem to be where variables that you would not have thought are slow do turn out to be slow. So are there new principles in evolved matter for what are the right slow variables? So that's another open direction. There's lots of others. I just thought to deliver what I promised, I should at least give you one slide on tomorrow. And this is my slide. And with that, I don't know, I guess this, yeah. With that, I close. Thanks a lot.
The small amount of drivers corralling a whole bunch of beats, I mean, we know it can be done. A few cowboys can wrangle a whole herd of cows or whatever, but they are talking to each other not just through the beats, but they have signaling in some other way.
Although in the 19th century, those guys, the guys about whom the Western movies were made, didn't have that.
No.
I mean, cows or the cowboys?
The cowboys. So I mean, a bunch of sheepdogs can
yeah.
flock the sheep but they're signaling to each other in some other way, not just through the motion of the sheep. My question is, can your in your system, can it happen without confinement? It seems to me that it needs the confinement of the annulus.
So, okay, I didn't show you, I guess, 2D. No, you can get the same structure in 2D, and you get long straight lines. And the reason is that these rods have a strong tendency to align with each other. So, in fact,
you did show me.
Maybe there was a picture there. So, you can more, it's not as great in the 2D, but you get very long rows of particles pushing a whole row. So that's a little different also probably from the sheepdog problem in the sense there you really, even in the two-dimensional case, you still have only one or two corrallers doing the work. So I don't know what so in 2D, if you have only one or two of these guys doing the pushing, then you will get some structure, but you won't be able to organize a 2D. I think you need at least a D minus one dimensional quantity of stuff to organize a D-dimensional thing, I think.
So probably you already answered it, but when you say D minus 1, I was thinking about D equals to 1. So is the problem of active matter at D equals to 1 level is trivial problem? Like
no, not really, because you saw that essentially this channel geometry you should think of as like D equals 1, because the width is finite.
Yeah,
and what we're thinking about,
even thinner and thinner.
You don't even need to make it thinner. You can just say, go to the infinite aspect ratio limit, and that's a D equals 1 problem.
Yes.
There's increasing, in fact, this relates to something else we're doing. I don't think it's trivial even in D equals 1.
Okay.
You probably can't, a few weeks ago I said you can't get flocking and you can't get condensation in D equals 1. Yes. I'm not even sure that's true. So I don't think it's trivial.
So one follow-up question is that now another variable in all of your problem is the noise.
Yeah.
So let me go to the limit where I go T to 0, noise is gone, quantum mechanics kicks in. What happens to all of this picture?
Okay, so now, then you have to, it's not these experimental systems. You'll have to look at other, so there are now, people have taken, for quantum condensed matter folks, imagine you've got particles which hop, so you have some, Hubbard model or something, and you have spin, but imagine that spin is not a two-state variable that this way and this way, but move this way versus move this way. You can write down what you might call active quantum matter. There's a paper recently from Roderick Meissner and company. And there what you have is Lindblad bath on these particles. They seem to see a phase transition in one dimension. I am suspicious of that result. We are looking at it, but it's not a crazy thing to look at. Yeah. And so it's different from this because you have to formulate the dynamics entirely in this quantum master equation language. And there's some beginnings of that work going on now.
It's like a Raman-Campbell quantum boxing.
Yeah, it is like that, but the point is there's a spin variable, and so there's a spin. You can think of it. There's a two-state variable which tells you which biases the movement, and there is an interaction amongst those two-state variables which make them align with each other, and there is so these are the things. So it's there. You can look. There's a paper by Roderick Meissner and company.
So, Sriram, I have a question. So, if you make it your rods polymers, will you see this? Some flexible object.
So, I mean, I don't know what will happen. People have looked at, as you know, people have looked at motile polymer problems. In this particular problem, I don't know what will happen. But in the 2D version, for example, if you had the rods connected like this, I think it will only enhance the effect. I think.
Sir, in the video where you have seen that flocking is happening in a flower shape. So if I am using a different boundary, say example circular boundary, so will the flocking still?
It turns out it's not that sensitive to that. With the flower geometry is something we were using for historical reasons because we were worried about particles accumulating at the edge. But actually, it's not a serious issue. In fact, it's better to not have that because it's if anything an unnecessary complication. Yeah, there is the edge does something. I don't think we've been able to make
because
this
at the edge, if a particle is following the edge if it follows the circular boundary, it can come out of the boundary. I think.
No, the scalloped boundary was chosen to re-inject particles into the bulk. It's not obvious that's essential, but one thing I'll tell you: this immobilized state, we've not been able to make that event happen without some help from the boundary. We don't really understand why. it may just facilitate turning or something. So it's a little dhila there. I'm not absolutely sure what the boundary does. Boundaries in general in these active systems are much more important than in equilibrium systems, partly because any motile particle eventually reaches a boundary. So in a time of order L, in a system of size L, you'll start to see the boundary, whereas other processes may take time of order L squared or something else. In which case, so finite size effects, boundary effects seem to be much more important in active systems. So that's generally a worry and an interesting issue. Do the simulation with periodic boundary conditions. So I mean, it's one of the annoying things about granular matter is that you can do bigger simulations than experiments. And so people will ask you, look, why didn't you just do a simulation? But it's okay. It's to prove a point of principle doing this. So I didn't show you much of the two-dimensional stuff. The periodic boundary condition means a flat torus. It's a zero curvature torus, right? And that can be done, and that's what the numerical simulations are mostly of.
Did you sort of get more like stationary islands surrounded by such?
Somehow it tends to produce one interface between dense and rarefied, and in that funny scallop geometry, we were able to, if we increase the number of rods, you get enough for 2 layers, and then they do this. In this other geometry, we weren't able to make it do that, and I don't know it's for want of trying or initial condition dependence or some other such perversity. But often, if you increase the numbers, you'll just get a pile, a bunch of stuff. You'll get a bulk domain of rods, bulk domain of beads, and behind the bulk domain of rods, a low density.
Okay, but you don't have entrapped regions like this.
It doesn't even in 2 dimensions. So I thought I don't remember if I had.
I was, thinking back of this old class of problems that you have coupled fields where there can be valleys in which particles can cluster. So that
I guess I don't have any of the 2D pictures here. Sorry. Yeah, it doesn't matter. But you don't get very dispersed. You don't get local condensate. I think the reason is that these rods. Supposing you just had motile particles which had a sense of which way they were going, but no particular tendency to align. Then what you tend to get is little droplets, little like micelles or little, where you get, where, I don't have that picture. So if you had things that were self-propelled, but had no particular tendency to line up with each other, then you get a blob of a little round domain of beads sequestered by a core of beads with a halo of particles, and that you get many of them. So I think this aligning tendency tends to just spread it out and make it one, and you finally pretty much just get one layer, bead dense, bead rarefied, because the aligning tendency.
Sriram, so maybe I missed. So in this problem of active turbulence, you had a motile particle in an inertial flow. Is that correct? Or
so in the very first one that I talked about?
Yeah, the first problem.
Yeah. So let me just go back. I went through that a little quickly. So this instability is without inertia initially, right? And then
But it's a motile particle in a
fluid. So they don't even have to be motile. It's enough if they're force dipoles. To get the instability, you don't make a turbulent. This thing makes the turbulent flow. You have a viscous fluid, you have a bunch of swimmers in it. You start with an aligned state, you perturb it. Right? So imagine these guys are all aligned like that. Okay, now imagine you perturb it. Then what happens is, because these guys are little dipolar force densities, they pull fluid this way here and that way here, thus pushing this guy further in the direction in which you perturbed it already. This is at the heart of the basic Stokesian instability of aligned active fluids, this and this. This process, however, if you include inertia, now has a lag. And what happens is that as a function of length scale, on a scale L, it takes a time of order L for an initial perturbation to grow by, let us say, 1 factor of E or something. And there's a speed there. There's an invasion speed. And that speed is set by active stress divided by mass density, square root of that. A stress over a density is a velocity squared. And that's the invasion speed of the instability. And if these guys are swimming fast enough, they can escape that. So, I mean, really, I guess I have it here somewhere in some later slide. Yeah, so if this is the scale of active stress and that is the mass density, then sigma A over rho turns out to be the speed at which the instability invades out to, okay. And V0 is the speed at which stuff is moving, so you can outswim your instability, but only if inertia is taken into account. So that's the thing. Yeah. Roop had a question.
Sort of a general question may be of importance to the fishing industry. So if fish are swimming from deep sea towards land, the depth is reducing. Does their active swimming, is it, do they communicate within them? Not communicate.
They've got to be able to sense that, I'm sure. Okay, I mean,
because there's a lot of tracking of these fish shoals.
So we actually wrote to some fish guys. 15 years back, we wrote to some fish guys. Some guy studying, some guy who was actually using the continental shelf as an acoustic waveguide and measuring the static structure factor of fish schools and fish shoals. And we thought, look, this guy should look at our stuff. He wrote back saying, oh yes, very interesting, but I'm very busy traveling. Sorry, that's the last I heard from him. So we were not important enough for them. But I think there's things to do here. All of that has to do with active matter, where inertia playing a very big role. And people have tended not to analyze, people tend to look at Stokesian systems where inertia is forget it, or really big systems where forget viscosity. But actually it turns out in order to suppress this Stokesian instability, you need really runners of order 1, not Barracuda, I mean, so there's a real crying need for experiments in this modest but non-zero Reynolds number regime. And there's a group, there's Daphne Klotza at North Carolina, has some system, is doing some work on this, but I don't think there's really a clean system yet.
Sriram, so here.
Yeah.
So the second part, you mentioned the similarity between active systems and dead inertial systems.
Right.
So the inertial system, what is the property? Are you giving an initial kick or is it driven?
So I mean, no, in inertial systems, you just imagine particles that are, supposing you've got particles you've got an imposed flow. So what's driving the system? So that's this stuff. I don't have the equations for the inertial system here, but imagine you've got particles in a fluid, okay? Then, roughly speaking, the dynamics of those particles in a fluid is mass into dV by dt plus viscous, drag into velocity relative to the nearby fluid is equal to other forces. That suitably embellished is the Maxi-Ridey equation. So what happens there is the imposed flow is the driver, okay, and that's what drives things. Here, the self-propelling motion of the particles plus the imposed flow are there, both of them are there. And the flow affects the direction of the self-propelled particles, and that turns out to be the crucial thing. And that allows it to have effects very much like centrifuging, which come from inertia. In this dynamics, what ends up happening is that the relaxation time of the extension of the particle, this dimeric particle, divided by the mobility, acts just like a mass for many purposes. You can map this dynamics without inertia almost exactly to the dynamics of particles with inertia. So the persistence time divided by mobility acts like a mass.
Okay, if there are no more questions, we would like to thank Professor Ramaswamy once more for a nice talk. And here is a small, I request Professor Umashankar to present Sriram with this small memento.